Hello everyone. In this video, we'll do a word problem for conditional probability. Here we have a bag containing 5 red balls, 20 white, and 15 black balls. 3 balls were drawn at random from this bag. So before we go ahead and set up everything, see what we are looking for, we have to make sure that we have an equiprobable sample space. So to have an equiprobable sample space in these cases, usually what we consider is that the balls are the same size so that the randomness of drawing is there. But to make the number of balls play a role and make the sample space equiprobable, we consider that each ball is labeled by a number. So we have red 1, red 2, red 3, and red 5 up and white 1, white 2, white 3 up to white 20 and so on. So if you have that, you basically have 40, so the total number of balls is 5 red, 20 white, and 15 blacks. This would add up to 40. And then we'll list all the possible outcomes here. Then that means that the number of elements in the sample space is going to be, I'm choosing 3 out of 40 distinct objects, yes? So that's something that we will use over and over again. Let's see what the first part of the question asks. What's the probability that exactly 2 red balls are drawn? So let me write this one. So we are looking for probability of exactly 2 red balls. Given that, knowing that, someone told us, seeing the result, that exactly one black was drawn. So exactly one black. Well, you can name these guys. So this one, I can write it as red, or this one as black. So it's obvious that we are looking for conditional probability because we know for sure that one black ball was drawn. Now we are looking for probability that 2 of the balls are red. So for that, I need to find probability of R intersect B and put it in the numerator, and then probability of B and put it in the denominator. But let's see what is the intersection of R and B means. So it means that exactly 2 reds and 1 black. That's the intersection. Yes. And here that means that I have to find the number of ways that we can draw exactly 2 reds and 1 black, and then divide it by n of s. Well, this is not that bad because we know that there are 5 reds, and I'm going to choose exactly 2 of them, and there are how many blacks? 15 blacks, and I'm going to choose 1 of them. And then n of s, as we already calculated, is 40, choose 3. How about probability that we need to put in the denominator, or probability that exactly 1 black? So exactly what 1 black means that, well, we choose 1 out of 15 possible or available black balls, and then the rest, there are 2 that we have to choose from the other balls, but there are both red and white ones. So we add white ones and red ones. White and red ones. That will give us, this is white and red. This is just black. We choose 1 from black balls and 2 from the rest. And then divide this by 40, choose 3. Okay, now that we have all we need, we can go ahead and find that probability of R, knowing B is, maybe I should have lower here so that I have enough space there. So in the numerator, the probability of intersection will appear. This is 5, choose 2, 15, choose 1, divided by 40, choose 3. And down there, this is 40, choose 3, 15, choose 1, 25, choose 2. Well, in all these calculations, when you're choosing or using an equiprobable sample space, you will see that in the conditional probability, the denominator of the numerator and the denominator of the denominator are going to be the same number. Both of them are going to be n of s, and they will always cancel. That's just something to keep in mind that should happen when you doing conditional probability. Now 5 choose 2 is 5 times 4 divided by 2. 15 choose 1 is just 15. There's only 15 ways to choose 1 out of 15 different distinct objects. This is 15 in the denominator and this is 25. I'm just using the formulas we have for these guys, choosing formulas, yes. Okay, so I can cancel that with the, the other way around, sorry. Should that gone the other way around? So this with that, and this whole thing here is going to be 10. So that is going to be 1/5. Oh, actually, there's another thing that I can cancel. This will go away with that one, and this will go away with this. There will be 12. And as you can see, there's now 10 in the numerator. In the denominator, I have 25 times 12. Well, you can do different ways, but this, there will be a 2. I can take out a 2 from that one, take out 5 from that one, and cancel that. And we get 1 over 5 times 6, which is 1 over 30. So the probability that exactly 2 reds are drawn, knowing that exactly 1 black is already drawn, is 1 over 30. Let's do another example here. So what is the probability that, okay, so let me write this. Probability that exactly 1 red is drawn, but knowing that, or given that, at most 1 black was drawn. Okay, well, I will use the same notations as before. So here for this one, I will use R. With this one, I will use B. But you know that they mean different things than the in part 1, yes? So here then I will need to calculate first what is probability of intersection of R and B. In other words, probability that exactly 1 red and at most 1 black is drawn. And for that, you should keep in mind that at most 1 means either no black or 1 black. So I can use the tree separating in different cases. So it will be exactly 1 red and no black. That will be one case. The other case would be exactly 1 red and exactly 1 black. And these are 2 different cases. And we know that for the first one, when we're trying to count, what we get here is that, well, we have 5 red. I want to choose 1 from that. And there are 15 blacks. I want to choose none from that. And, well, there are 2 left yet. And I have to make sure that I choose that from the white ones. Yes, there are 20 in total white, and the rest will come from the white. For the second part, I need to choose one from reds, one from blacks, and then the remaining, which is only one left, I have to take out from the whites. And then we add these two numbers. Yes, you know the properties of the tree. So this means that probability of R intersect B is going to be n of R intersect B divided by n of S, but that number in the denominator we already know that 4D choose 3 is the number 5 choose 1, 15 choose 0, 20 choose 2, plus 5 choose 1, 15 choose 1, 20 choose 1. So that is the probability there. Well, actually, I can make it a little bit easier or nicer look, give a nicer look here, but I will leave it like that because I need to do more calculations later. That's for the intersection. We need also to know what is the probability of the given part, which in this case is probability that at most one black is drawn. So for at most one black, again, you have two cases: no black or exactly one black. For no black, it means that I choose nothing from 15 blacks, and then the rest, the three, basically all three, will come from the both of white and red together. So there are 25 of those, so this is white and red. When there's one black, exactly one, I choose one from 15, and then the rest, which are two left, will come from the white and red. And then you add these two, and then that will give me probability of B is 15 choose 0, 25 choose 3, plus 15 choose 1, 25 choose 2, and then divided by 40 n of S. Yes, 40 choose 3. Now that we have both of these guys, then the probability of R given B is going to be, well, the B is here. I won't write 15 choose 0 because the whole thing here is just 1. So we'll write 25 choose 3 plus 15 choose 1, 25 choose 2 divided by 40 choose 3. And in the numerator, we have 40 choose 3, and what is, okay, 5 choose 1. 15 choose 0, I won't write that, and write 20 choose 2, plus 5 choose 1, 15 choose 1, and 20 choose 1. And as you can see, these cancel. You can do more work there. For example, this guy is going to be 20, 15, 5, in general, n choose 1 is n, yes. But I won't do all those calculation or any simplification, and I will write it as it shows it here. So 15 choose 1, 20 choose 2, 5 choose 1, 20 choose 2, plus 5 choose 1, 15 choose 1, and 20 choose 1. Yeah, so that's how you bring in the equiprobable sample spaces and find the probabilities of each part of the formula for the conditional probability and calculate the conditional probability in situations like this.